class, we're going to have 3 little videos for section 7.6. This first one is going to be our motivation. The second one will be the meat of 7.6, and the third we will continue with this example to do that one fully so that we have something to look at as a demonstration. So let's compare what we're going to be doing here with what we just did in 7.5. So in 7.5 we were looking at an x-bar distribution, and it was approximately normal when our sampling size was at least 30, or if the parent distribution x was already normal. So the advantage was in situations where we could make x bar be a normal distribution or approximately normal distribution. We have lots and lots of tools like our z-table that we can use to figure out particular probabilities. In this case, we're going to make another normal approximation, but in this case we're going to be starting with the binomial distributions that we saw in chapter 6. So let's look at this particular example that we're going to be exploring after the body of the content. So here we have a landlord who must install 50 water heaters. From past experience, she knows that the probability that any one of them will last at least 10 years is 0.25. So the question is, what is the probability that at least 16 of these water heaters will last at least 10 years? So how do we approach this? Well, turns out that this can be looked at as a binomial experiment. Any one of these water heaters either lasts at least 10 years or doesn't. So there are 2 possible outcomes for any one of these water heaters. So we need to consider the usual things when we're looking at a binomial experiment. So in particular, what is success and failure, and what are their probabilities? So success, S, is that the water heater does last at least 10 years. So failure is its complement. S does not happen, so the water heater does not last at least 10 years. Their probabilities are given by P and Q respectively. So what is the probability of success? So we're looking at, for any particular one water heater, what is the probability that it will last at least 10 years? We look up here. We see it's 0.25. So P is 0.25. So what about Q? S and F, success and failure, are complementary events, so their probabilities must add up to 1. So Q is 1 minus P. So that is 1 minus a quarter is 3/4. So the probability that a water heater does not last at least 10 years is 0.75. So N, what is N going to be in this case? How many times are we looking at, how many water heaters are we looking at? 50 water heaters. So our N is going to be 50. These are 50 independent trials. Each water heater lasts at least 10 years or does not last at least 10 years. So the question is, what is the probability that at least 16 of these water heaters will last at least 10 years? So we need to know, what are we asking about? The number of successes are at least 16. So that means greater than or equal to 16 is what we care about. So the question can be phrased, what is the probability that R is greater than or equal to 16? Okay. So there's our data again. So fine, we use our binomial distribution, our binomial probability chart, table 2, but for us, this chart's not going to help us because our chart only goes up to n equals 20. If we had a bigger chart that went up to 50, that would be great. We don't have access to that. We need n equals 50. So we're going to do it by hand. So let's look at the top. Let's remind ourselves, for any probability of R of a particular value, we have n choose r times p to the number of successes times q to the number of failures. So n minus r, many failures. So for us, we're interested in p of r is greater than or equal to 16. That means we care about p being 16 or 17 or 18 or 19, all the way up to 50. So we would have to do many, many, many calculations. Certainly possible, but kind of a pain in the neck. That's why we used our table in the first place. Okay, so we can do this, but we have an easier way to do this. What is the name of this section? Normal approximation of the binomial distribution. So we're going to be able to normally approximate this distribution. Okay, so we're going to look at the next video and see exactly when we can make our binomial distribution look like a normal distribution. We'll have to make what we call a continuity correction, and then we'll be able to use our z-table to figure this out. Okay, so now take a look at the next two videos.